Hello, my name is Dr. Ken Amor. I work here at St John's College, Oxford, and today I'm going to be talking about copper exploration. But first, a little bit about me. I started off studying geology at Reading University, then went out to work as a geologist for a little while before returning to university to take a master's degree in geochemistry at Leeds University, followed by a DPhil or PhD here at Oxford University. I then went on or stayed on at Oxford doing research, teaching and outreach. So copper is a transition metal element. It occurs in the first row of the transition metals. It has an atomic number of 29, meaning that it has 29 electrons and 29 protons. It has an average atomic mass of 63.5. It's an average because there are two naturally occurring isotopes, where an isotope is simply an atom of an element with a different number of neutrons, giving it a slightly different mass. So this resurgence of interest in copper in recent years is partly to do with its electronic structure. And this electronic shell diagram on the right-hand side is a kind of simplified version, probably in a format that you're not really used to. But the important take-home message here is that in its outermost shell, it has a single electron. That means that in a metallic crystalline lattice, copper makes an excellent conductor of electricity because that electron can be passed from one atom to another. And electricity is simply the movement of a charged particle. That single electron in the outer shell also makes copper a very malleable metal. Malleable just means it's bendy and doesn't break very easily, which are the sort of properties that you need in an electric cable or a wire that conducts some electricity. Having that flexibility means that you can bend that wire to whatever kind of shape that you need. So hence copper is important for the transport of electricity, and it's also used in the electronic industry as well. So silicon chips or microchips will usually have a silicon wafer over which there's a thin layer of copper is deposited, which can be easily etched into an electrical circuit. So copper will power the green energy revolution to replace carbon as an energy source. Because each wind turbine uses copper in the electrical generator, each solar panel will be connected to the national grid by a copper cable or wire, and each electric vehicle will have an electric motor that will use copper as its core. So hence there's been this renewed interest in copper, and it's regarded as a strategic element. So copper is a raw material that has to be mined and processed and refined, just like many other raw materials. But on average, it's only found, or the Earth's crust only has, on average, 0.006%, or 60 parts per million. If that was our only source of copper, then we'd have to process a huge volume of rock in order to be able to extract this valuable material. But fortunately, there are certain geological processes which we now understand that concentrate particular elements, such as copper, into mineral ores, which make them more sort of highly concentrated. Unusually, and there are only about 3 or 4 other examples, copper can occur as a metal itself. the other metals being silver, gold, and also mercury. But that's quite rare, and most of the sort of native or natural copper has been sort of found already. More typically, copper occurs as a sulfide in a mineral such as chalcopyrite. So that will be in combination with iron as well, or as a carbonate in the mineral malachite, or as an oxide such as the mineral cuprite. These are the sorts of mineral ores that geologists and mining companies will look for because they're sort of highly concentrated forms of copper, which means that the environmental impact of the mine can be kept to a minimum. So this is a map showing the distribution of known copper belts, known sort of copper deposits, as shown in red. And as you can see, it's not entirely random. There seems to be some sort of pattern because they occur in these relatively thin bands or strips or ribbons. And in particular, there's an association with plate boundaries. So the Earth's crust is divided up into a number of tectonic plates, which are moved about by mantle convection currents. And where plates collide, particularly where an oceanic plate collides with a continental plate, that crust will be pushed beneath or subducted beneath the continental crust. And so there seems to be an association between plate tectonics and where we find copper. So let's explore that in a little bit more detail, taking as an example the Andes mountain range. So the Pacific plate is moving towards the right, as in this cartoon diagram, and the oceanic crust, being a little bit more dense than the continental crust, will get pushed under the continental crust in what's called a subduction zone. As it does so, as it moves down deeper into the mantle, it heats up. It'll also heat up because of friction between the edge of the oceanic crust and where it's rubbing against the continental crust. And part of this oceanic crust, which will have a layer of sediments, which will also contain quite a lot of water, of seawater in it, will start to melt. So you'll get partial melting, and that melt material will be very light, low density material, which will rise up through the continental crust. And this will form quite large intrusions, typically of a material such as granite. And if it eventually reaches the surface, it will erupt as a volcano. And this is the sort of typical geology of what you find in the Andes in South America. So copper porphyry deposits or copper deposits are associated with subduction zones, and in particular with these large igneous intrusions. So copper porphyry deposits, as they're known, occur above, or typically occur above these large granite intrusions, and they form from an offshoot of material above the granite. A granite will typically be made up of silicate materials, that's silicon and oxygen, combined with some metal cation, typically calcium, sodium, or potassium. And there'll be minerals such as quartz, which is pure silica, feldspars, which will be typically something like a sort of a sodium or potassium silicate, and also micas. Copper doesn't really form or doesn't readily form a silicate mineral. but it will react with sulfur to form a sulfide mineral. So copper doesn't really form within the granite. It's part of the sort of leftover material. Because there'll be also be a lot of water, it will set up what's called a hydrothermal or sort of hot fluid that sort of comes off the granite as the granite cools and solidifies. And this hot fluid can carry all the elements that don't readily go into the to the minerals formed in the granite, and they'll be precipitated as in this instance, as an enriched ore of copper. Those hot fluids will also move out through the rocks, particularly if those rocks to which this granite has been intruded are sedimentary, because they'll be very porous, have lots of fractures in them, and these very hot fluids, as they pass through the rocks, will produce a mineral alteration. But they'll do so in a way which is dependent upon the temperature and composition of that fluid. And as you progress away from this igneous intrusion, the fluids will cool down and you'll get a different mineral assemblage replacing the existing material in the rocks. That means that you'll get this typical alteration zone, and you'll get zones of different minerals, some of which are very important to geologists when they go looking for these copper porphyry deposits. Another process that enriches the copper ore is water coming from the surface. So it'll rain on a particular area. Some of that rainwater will soak into the ground, forming groundwater, and will accumulate in a water table at some point. As that water moves down through the rock material, it will oxidize the sulfides, such as chalcopyrite, this sort of copper sulfide, oxidizing it, leaching out some of the copper, which then gets reprecipitated as other minerals, such as malachite and cuprite. So this will give a secondary enrichment of secondary minerals, which are also very rich in copper. So there are two processes going on within a copper porphyry deposit. There are these hot hydrothermal fluids that comes from which will carry and transport leftover material from the formation of the granite. And then there's this cooler, colder groundwater that soaks into the ground, oxidizing some of that sulfur material, or the sulfide material, and redistributing some of the copper minerals. So how do geologists look for copper? So unfortunately, most of these copper porphyry deposits will be covered over by later sediments, meaning that particularly now, it'll be very rare that you'll find a copper porphyry deposit exposed at the surface. Therefore, geologists have to act like a detective, looking for different clues, piecing together all the information. A good starting point will be a geological map. So this is likely to show areas where you'll find some granite intrusions, some of which will be exposed at the surface. Actually doing surveys and looking for these mineral alteration zones and mapping those, including those onto geological maps. Another way is to use magnetic surveys, and I'll talk about that in a little moment, and also sampling, especially stream sediments. Okay, so magnetic surveys. So the Earth's magnetic field isn't uniform over the entire surface of the Earth. It can be altered depending upon some of the material within the Earth's crust. In particular, there's a mineral called magnetite, which is an iron oxide. And as its name suggests, it is, or it can be, a very magnetic mineral. Magnetite can be found in two sources. One is within an igneous intrusion, and so you'll get a little bit of magnetite in a granite. But the other source is, again, it's one of these hydrothermal minerals that's produced from these hydrothermal fluids reacting with existing minerals or transporting iron in these sort of hot hydrothermal fluids and precipitating them in zones associated with an igneous intrusion. So in typically magnetic surveys can be conducted airborne, so you carry the instruments in an aeroplane and you just fly backwards and forwards over a particular area and mapping the magnetic response, or basically it's mapping the Earth's magnetic field, whether it's slightly weaker or slightly stronger. And magnetite will produce a very strong magnetic response, whereas other rocks such as a sandstone, which might contain very little iron, will produce more of a sort of negative anomaly. So this is what we're looking for. We're looking for these sort of positive anomalies, which can give an indication at least that it might be one of these two sources of magnetite. And so then the other way that geologists can search out some of these copper porphyry deposits is through stream sediments. So water and anything that water carries will move downhill, downslope. That means that if you search through some of the stream bed material, the sort of sand and other material found in the bottom of a river or a stream, and look at the mineral composition of that, if you find a mineral such as sort of pyrite, for example, it's a good indication that there will be a source of pyrite further upstream. And one can go sort of map out all these streams and the amount of pyrite that's found in them to work out where some of this material might be coming from, which will give you an indication of where one might find some of these alteration zones altered by these sort of hydrothermal fluids. Okay, so that's a very quick overview of copper and mineral exploration. If you found this interesting, there's further information on our website. And why don't you try out this porphyry exploration game to have your own go at being a mining geologist, to see if you can find the best place in a particular area which is marked out in the game as to where to look for copper. Thank you.